ME 218. That was not the question. The question is, what is absolute maximum shear stress? Yes or no? Absolute maximum shear stress, that means you have to decide where is sigma z or sigma c is. No, everything depends. If you remember the discussion we had, everything depends not only onto this principal stress P1, but this is sigma P2, also depend on sigma C, because we are going to change that in future classes. I gave you a couple of examples. The sigma C was not equal to 0. Remember, we put it under the water or in the sky, sigma Z. So when you draw your Morse circle, which presumably end up half of it being on this side or half of it on the other side, like that. The next, this is, if you write R equal to tau, many people write it like that, a number. That's exactly what you were doing in ME 218. Everybody understand that? Here I went about a week for a class or half showing all those pictures, in plane, out of plane, everything that we comes in today's discussion as well. So therefore, you have to decide, okay, this is my tau max, in plane tau max, yes or no? What is this the absolute maximum? You have to prove it for me. However, some of you may know the answer, some of you I don't. But if you don't put anything down, so I don't know what your answer is. Some of you draw this one. Fine, I accepted that because you are already know it. Some of you put sigma c equal to 0, but all of them saying the same thing. In this scenario, since sigma c is equal to 0, because we are in plane stress, nothing coming from this side of the bracket. As you see, this is the bracket on a car connection. Is that correct? Wheel connection. Is that correct or not? Since that's the case, therefore, sigma, this is principal 1. This is principal 2. This is principal 3, which is 0. So you have all 3 circles, and based on that, this is maximum. But I didn't subtract too many points for that one because everyone threw that through the process, but you did not show me that. So that I probably subtract about 3 points there. Is that correct or not? Now, going to the second question, the same problem happened one more time. I did not ask you to calculate stresses in the x prime direction and y prime direction. Look, the question is not that. The question is, let's say there is a part of machinery, and let's say that here is part of machine. I don't care how the machine looks like. And in this direction, you find some flaw or something that you are interested to find the stresses in that direction. The stresses in that direction is this and that. Yes or no? Yeah, but this is not sigma x prime. This is sigma. Look at my answer in the solution I gave you. That is sigma y prime. Not many people mentioned that. About, a few percentage of the class understood the question. Because read the question carefully. It says, it is in the question, the stress perpendicular and parallel to that line. That could be a welding line. It could be a crack there. It could be crack appeared there, and I want to know what the stresses causes that crack. Certainly, it is not, as you see that, just for you to understand what you are doing, I ask you to plot it on there. This is sigma x prime. Everybody understand that, yes or no? But the direction is here. Is that correct? So the answer to part 2 is sigma y prime and tau x prime. Many of you did not calculate the sign correctly. That's why I pointed out in this one, in order for you not to make that mistake again. This is the whole idea. I gave you this solution. Notice your x prime is positive, your y prime is negative. So if x prime is positive, it means it must be going this way. Is that correct or not? Yes or no? Going with the arrow, correct? And if the y prime is negative, it should be going like that. So if that you end up like that, this value is negative value, yes or no? For that one, I may have subtract 1 point. So not many people put a minus there. So the shear value there is minus, not plus. Is that understood? Yes? So what I'm saying that I'm not going to repeat that question the way we did it in ME 218. We are doing that based on material we learned in ME 219, which were in plane, out of plane. Is that correct? The 3 circle. Not very many people attend. And it comes to the final, the same thing you will see in today's discussion. Everything is based on not maximum shear. Everything is based on the absolute maximum shear, which you have one of the 3 circles. Is that understood? Yes, it's very important. You will see it in today's design. If you understood, that's why I'm stressing that point. That's why I'm asking you to get you prepared for discussion like today's discussion. Is that understood? So please, that's why I gave you. If anything missing in your quiz, not written like what I have written there, the rest of it is, of course, typical of finding the Mohr circle, etc., etc. You should not have made any mistake in your sign, etc. So many people even don't draw still the circle. You need to do that anyhow. Let's go now to the design of a beam. So we are going to have two types of the beam discussed today. The discussion is, first of all, is the beam design and the shaft design for today's lecture. Hopefully we'll continue. Unfortunately, I cannot finish it today, and I have to continue with that on Thursday. For that reason, I'm going to postpone your quiz and your homework until next Thursday, because I know some of you already have done it. I saw at least 5, 6, 7 people in the office hours that they have done. Even they went ahead did the shaft design without me telling them what's going to happen. But in many cases, you have to wait until you really understand the detail of the work, not for the purpose of this class, for the purpose in general, understanding what's going on. Is that correct or not? So on that basis, because I'm going to be a little bit behind, I'm going to postpone that. And it is near the midterm, so we are going to skip one quiz anyway. I always have done it in the past. So just let that be the one. Okay? So your homework is due for Thursday. Is that correct? On Tuesday, I'm sorry. Your quiz will be next Tuesday. All right? Okay. Now, beam design. Now, beam design, we are going to talk about two types of the beam here, beams. One type is the rectangular cross-section. If we have a rectangle, write it down. This is rectangular cross-section. Notice when we have a rectangular cross-section, obviously sigma equal to, on top and bottom, sigma equal to plus minus MC over I. Correct. The tau is equal to what? The tau is equal to VQ over IT. Plus minus, depends on the direction of the shear for IT. But last time I gave you a simplified version of that one. Yes or no? Do you have it in your note? Yes? You see 3 over 2 V over. If I put this for rectangular cross-section, because this is a specific case, write it down. Write it down, rectangular beam. I wrote it down on the board last time. This is for rectangular cross-section. You see that the top one is rectangular, the bottom one is the white flange beam. I'm going to discuss all of that together. So this is typical, but for the rectangular cross-section beam, this ends up to be like that. Is that correct? This is only tau max, which is on the neutral axis because T is constant. Is that correct or not? Yes? And then, okay, so we say to that, then what will happen after that is very important. Okay, we calculate maximum normal stress. We calculate maximum shear based on your shear and moment diagram, yes or no? But that's not the end of the story. This is what we did again in ME 218. Now you are ME 219, and I'm going to make it a little bit more sophisticated, yes or no? I want you to pay attention, all right? Because that's the whole thing. If you do not pay attention here, you are going to miss it in your quiz. Is that correct or not? Now, what happened here is very important. As I said it last time, in any beam that you look at that beam there. If you have a beam there, is under the loading P, this is the simplest it can get. So, and you are here, of course, you draw the free body diagram of that part, left-hand side. You have a reaction here. Therefore, you have here shear force, and you have a moment there. Okay, on the top, so in the top, you have a normal stress and no shear stress, yes or no? According to these two formula. Yes, shear stress was 0, normal stress is there, so I have to go there. I don't want to draw it here. So if you go there, you see what I'm talking about. So you will see on the top of the beam there. So I don't know if it is on or not, or is it working or not, or run out of battery. Yeah, look at the top. This is a normal stress in the form of compression for this beam, yes or no? Is this principal stress or not? See, all the knowledge of principles. This is why I'm insisting that everybody should know all the principles. This is principal stress, yes or no? Because shear is 0. However, there is a shear associated with that. We are going to discuss it in a minute, what's going to happen there. On the bottom, this is principal stress, yes or no? But in between, are these principal stresses? No. So I need that. Those require a principal stress, yes or no? So this is how difficult the beam design, as simple as that will be, that I know what the principal stresses on top, but I need to know the principal stresses for any point in between, yes or no? For that reason, knowing this is going to happen in this beam or that beam, we only talk in ME218 of the top point and the middle point and the point on the neutral axis, yes or no? On the neutral axis, usually there is no sigma. Of course, if we have an n, there is a sigma there as well. Everybody understand that, yes? For this typical of this, what I drawn here, that like that, for typical of this scenario, this is maximum sigma, this is maximum here, this is maximum shear, which is vertical, yes or no? Let's now explore that in detail, going to the next page. So go to the next page of your handout. So I go the same thing here. I do this numerically. I did it for the other class. I do it for you guys. So let's go to the next page. Oops. Where was it? Here. You have your handout. If anybody missing a handout, I have a couple of extra one here. Anybody need the handout? Yeah. Just... these are all I have. Okay, share it together. I gave you this long time ago. There is a beam there, yes or no? Correct? I don't know. You see it here. Is that correct or not? Look at that beam there. There is a simple beam there. You don't have to worry about it. It is. I just had a few extra ones, so I thought I'd give it to you. So what do you do with these pages that I gave you? Throw it out? You keep asking for another one? What's happening? I don't know, all the handouts. You are supposed to print your own. Remember that? Okay. Okay, now pay complete attention to what's happening here. Look at that beam there we are having there. So when I draw the free body, like here, if I draw the free body diagram of this left-hand side of the beam, we are checking all the stresses in this just for the purpose of discussion. You have to do your own anytime you do the design. Look how much calculation has gone there into that analysis. This is, the force there is how much? The force is 3,600, yes or no? The reaction is, the left-hand side is 3,600 pounds, and this distance is 9 inches, yes or no? Is that correct or not? Therefore, in this cross-section at 9 inch, this is what they are asking us to do. This is just for purpose of, again, showing you what's happening. So you have a shear force of 3,600 pounds going down, yes or no? You have a moment which is 3,600 times 9. Action is here, the reaction is there. Is that correct or not? So that's the here. And that one become equal to 32,400 pound inch. In other words, the shear force is equal to 3,600 pound going down. The M is equal to 3,600 times 9 equal to 32,400 pound inch of moment, and it is plus because it's going like that. Compression on top, tension on the bottom. And this is what we were doing on all the time in ME218. Yes or no? So far, so good. Yes? Then, of course, you have to calculate the I. A we don't want. We need to calculate the I. I is depend on the cross-section. Look at the cross-section there. It's 6 inch by 2 inch thickness and 6 inches high. Yes or no? Correct. Therefore, the I is equal to 112 of base, which is 2 inches, times 6 to the power of 3. So you get that one equal to 36 inch to the power of 2. And now we follow that with what we learned in ME218. On top of the beam or on the bottom of the beam, one is plus, one is minus. Let's go to the top, for example. Sigma on top, of course, equal to minus because it is in compression. You are here. So that is equal to minus M. M is given 32,400 times C, which is 3 inches because the total length is 6 inches. So the C is times 3 inches. Correct? Yes, divided by I, which is 36. So as you see there, it becomes equal to minus 2,700 PSI. Yes or no? Yes? Correct? All right. Now, I want you to put a piece of paper, cover this part. You see that part there? That's what I'm doing. This is what you were doing in 218. Everybody understands. You cannot cover this one. I have to cover it there. So here it is. I cannot even cover it there. No, okay? Is that correct or not? You cover the lower part. Is that correct or not? Because I don't want you to get confused. This is what I'm calculating. So on top, look, on top, you have a state of stress like this. Yes or no? Correct? And that is equal to 2,700. Yes? Where are the circles? Or circle or the circles, all three of them. Yes or no? Okay? How do you draw that? Come on, guys. We are spending 2 weeks on the circle, and now you should be very good at it, and I'm sure you know the answer. These are first of all, are these principal stress or not? Yes. So it's the principal stress. It's very simple. This is minus 2,700. The other one is 0. That's 0. Is that correct? Principal stresses should be on the sigma axis. Yes or no? No tau. Tau is 0. Correct? So this is your circle. Yes? Sigma is 0, so the other one circle is here, the other. So this is principal 1 or principal 2. This is principal 1 and principal 3. Is that correct or not? The other circle is 0. It can be. Is that correct or not? Yes? The circle sometimes become a 0 if the sigma 1 and sigma 2 are equal. Is that correct or not? Therefore, that's the case. So, however, what's the maximum shear here? You see? Now, going back to this method, if I calculate shear here, let's do that first to understand what happened here. In this one, you calculate the top 2,700 in compression. The bottom will be what? 2,700 on tension. And the distribution is linear. Yes or no? Correct? But here, the top shear equal to what? 0. On the bottom, shear is 0. At the middle is how much? I already gave you the formula. At the middle, the shear maximum shear is 3/2 shear force over the area. Let's calculate that one. So what I'm saying that as soon as I calculate sigma on top, which is the maximum normal stress according to, let's calculate tau. Tau max on the neutral axis, is also equal to plus or minus, doesn't matter for timing. It's equal to 3/2 B over A, which is equal to 3/2. Shear was how much? Shear was 3,600 divided by area. Area is 6/2. So you calculate that one. That becomes 450 PSI. Is that correct or not? Yes? And that is what you see on the graphs A, B, C. This is the cross section. That's the free body diagram. That's the normal stress. That's the shear stress according to what you learn in ME 218. Yes or no? The rest of it is now 219. That's what I'm saying. They have to pay attention there. Now, this is what the discussion is. In 219, we'll learn about all of that. Notice, maximum shear stress according to this formula is there. Is that correct? Going vertically. Yes? But look at this graph. Does it have a maximum shear here? Yes or no? Yes? Isn't that normal stress? Is this maximum shear here? What's the maximum shear here on the top? Tau max equal to what? Tau max equal to half of diameter of the circle or half of 2,700. Yes or no? So if I calculate that in magnitude is equal to 1,000, it is 2,700 PSI divided by 2 or 1,350 PSI, which is much larger than 400. Where is that? Is it in vertical plane or is it at 90 degree with respect to the principal? Here 90 degree with respect to principal. Here will be at what? Here will be at 45 degrees. So that in this beam, a crack going to appear on the top at that direction, not because of 450, because of 1,350. Did you see that? Because now you are considering everything, all the circle, more circle, everything. Actually, that's the shear that you have to worry about. So on the top, the shear is that. As you see, you can look now here. Look at the top portion. This is 0. One principal stress is 0. One principal stress was minus 2,500, but absolute. This is the absolute maximum shear. The absolute maximum shear is how much? 1,350 according to the Mohr circle. Yes or no? Did you get it? quiet. Yes? All right, this is a circle, and a circle, everybody knows if this is principal stress, this is maximum shear. And these two are at 90 degrees. So if this is principal stress, I have to go 90 degrees here. Here, I have to go 45 degrees, so that shear is here. Is that correct or not? But that's not 450. That is this much. Is that correct or not? 1,300. Totally things has changed. So as you see, you have to worry about that part, not any part. So therefore, this is it. Now, for the bottom, we did the same thing. So that's for the bottom. So you go there, it becomes reverse. This is one principal stress become tension. The other principal stress becomes zero. This, as you see, going through all this operation for every point in between. For the other point, I have in between, I have to draw the Mohr circle. I'm not asking to do it. They have done it here. Everybody understand that. So when you go to this point here, they call this point point A, this point point B, this one point C. This is B. Let's go to point C, for example. On point C, this is the stress for point C. You have a sigma. Granted, this sigma is less than sigma top. Yes or no? Correct? But then you have a shear stress, yes or no? I'm sorry, the shear stress due to the shear force, yes, correct or not? Now, is this combination is a principal stress? Then you have to draw the Mohr. Look how difficult this task becomes. However, when they did that, look at point C, for example. One stress is, it's hard to read that, it's in your handout. One stress at point C, one principal stress is 152. The other principal stress is minus 1052. So they make the story short for you to make you happy. Let's put it this way. Which point is the most critical point in this beam? Look at all the things. Look at the net result. The net result is in D, E, and F. Is that correct or not? Which point do you think is the most critical point? Only top and bottom, nowhere else. So discussing all of that to show you what's happening. But the result is to our advantage. That means I don't have to check anything else except top and bottom. So please write it down. If it is a rectangular cross section, you have to check only the top and bottom. However, be careful here. You don't check it for this principle of 450. Remember that? You will check it for half the sigma on top. That is much more larger than the vertical shear. And it's not vertical shear. It is at 45. The vertical shear is in this plane. Everybody understand? The shear is now at 45 degrees to that. Yes?
So that formula is just for tau average, right?
No, it is tau. That formula, the 3/2, is only for tau max. For the other one, that's only for tau max on the center. I use that for the center. That's what I use it for this formula only, for 50. It doesn't apply to the other one, no. For the other one, you have to use this technique. That's the question he's asking, guys. For that one, because I use this height and this, that's for them. For any other point, you have to use Q, etc. 3/2 is not constant. The shear stress is not constant. It's changing. Look, the shear stress keeps changing.
If it's average, because it's the...
No, it's not average. You forgot. I did it last time. For the tau max, I put the height equal to h/2, and I calculate Q max, and I calculate tau max, which is usually when you design it, you want tau max.
It was just confusing because you were saying tau max for both.
No, that tau max is for VQ over IT. This is this graph. Look at that graph. Look at graph. You see there, his question is referring. You have to understand all of this. That graph, what you are referring to is part C. Look, graph C. What's graph C? Look, shear on top is 0. Here is 0, and it changes parabola. What is the maximum? The maximum is on the neutral axis. Is how much? Look at it. 450, which is how I calculated. Okay. Did you see that? Yes, it's not tau average. It's just on the max. But if I want to only to consider this, I should consider 450 in this one. That's not the critical point. The critical is 1,350 on top. 1,350 is larger than 45, but it's not in the vertical plane. In the vertical plane, actually, it's 0. It is at 45 degrees to it. So the crack that start in the beam always start because of the shear start on the top at 45 degrees. Check it next time. Any beam you see, concrete beam, wood beam, usually the crack, you look at all the beam, it's like breaking, the crack is on top, is at 45 degrees because they fail in shear. And the shear is maximum on top. Is that correct or not? Which is, by the way, half of the normal stress. But the normal stress usually does not cause a crack for this kind of. Is that understood? Yes? Correct? Because now we are considering everything. Is that correct or not? Now, based on this scenario, let's go to the next example. Everybody understand that? Although I did all of that, we end up that not to worry about, for rectangular, you should write this down. For rectangular beam, you should not worry about any other point except the top point, but based on the Mohr circle. Everybody understand? You get your tau and you get a sigma based on the Mohr circle on top and on the bottom, which is the same thing with different sign. Is that correct or not? Yes? Now you have to look at this picture. This is considering the whole idea of the principal stresses. You have done a table on the bottom, shows all the principal stresses. By the way, there are color picture, showing the direction of the principal. This is so complicated you wouldn't believe. The direction of the principal stresses keep changing here. This becomes graphically very complicated even to show. Is that correct? There are some color picture of that one. If I have time or sometime I'll bring it and show it to you. Is that correct? But you don't have to worry about it. That's just show you how complicated things can get. Is that correct or not? For you as a designer, for the rectangular beam, you just check the top and on the bottom. Is that okay or not? Yes? Now let's go to the second type of the beam, which is, this was rectangular design. Now go to wide flange beam. So let's see what the wide flange beam design are concerned. So if I go to the wide flange beam, you have seen this before. This is what we call wide flange beam, by the way. This is called web. This is called web. And these are called flanges, one on top, one on the bottom. These are wide compared to this thickness. This thickness is small. This one is broad. Again, sigma is the same thing. If I have a beam like that, as I showed you on the previous picture, the same thing happened here in previous picture. So you go there. As you see here, there are several points here on top and the bottom. On the top, it is maximum normal stress. On the bottom, it is maximum normal stress, no shear. The vertical shear is on the neutral axis again. Yes or no? However, things get a little bit changed there because when we come to the sigma, we use plus minus MC over I on that here or there. Is that correct or not? Yes? For the tau, I have to use tau equal to, again, VQ over IT. Yes or no? Correct? Which is very difficult to calculate for that one. Now, you remember from discussion we had in ME 218 that we started here. Generally, we should go like a parabola like that. Remember, for the rectangular shape, we get a parabola. But here, we don't get a parabola. Why? Because there is a break here. Yes or no? You see that point? An epsilon above and epsilon below. This thickness usually is very large compared to this thickness. Yes or no? This is the thickness of we call it thickness of the web, TW. And that is the width of the beam on top. Everybody understands. If this is, for example, is equal to 12 inches, this is 1 inch or less. Everybody understands. Therefore, when we calculate the stresses like before, from here up to here, that parabola comes to this point. At this point, suddenly I have to go from 12 inch to 1 inch. Everybody understand that? If I suddenly change this from 12, let's say I put here 12, and I get 100 psi. If I make this 1, instead of 100, I will get 1200. Yes or no? Suddenly, it becomes much larger. Yes? You have seen that in ME 218. Therefore, this jumps for this ratio I gave you. If this is 100 psi, this becomes 1200 psi or become much larger. And then as we go down, the Q change a little bit, not much. Still, the Q max is on the neutral axis. And then goes, again, the same thing here. The same thing here. And then goes like that. As you see, the bulk of the shear stress is taken with the web. Is that correct? Not the flanges. So really the way they designed this, the flanges are for normal stresses. The web is for shear stress. Everybody see that because 97, 98% of the shear stresses go to the. For that reason, according to today's code, American Standard Code, this is for American Standard wide flange beams. So please write it down. This is W beams only, not any other beam. If you go in the factory, you put 3 pieces of steel together and weld it together, any side that does not qualify. These are the beams that you have to buy from manufacturer, and there are all the code people are sitting in Pittsburgh and New York. There are thousands of people working on this based on the American Standard steel. Everybody understand what I'm saying? That's why you cannot buy even the steel from other country and bring it here unless it should be checked by the authority to see whether it's qualified under this rule. Everybody, we have lots of rules, not 1,000 and 1,000, and they have to be qualified. This is one of them. Is that understand what I'm saying? That if it is based on American Standard, you can use this instead of that equation. You can use this equation that the shear stress from here to here, which is constant, as you see here, is equal to shear force divided, we call it area of the web. But since this is too conservative, they consider area, although the shear stress is here, but for the average, they consider area of the web, not of this height. They consider it this D, that's just, this is the way code is, D times thickness of, in other words, they consider this as a web because they don't want over-stress this sort of thing. So the time D, which is the depth of the beam, times thickness of the web. So if you see on the solution manual, this has been used, and you are supposed to use it. Anytime you use one of those wide flange beams in the back of the book, or any of them, you use this equation rather, because the other equation doesn't work. Yes or no? As you see, the bulk of this, assuming this is constant, because this is a little change here, all of this is going there. Is that correct? And since you are using later on a factor of safety of 2, 3, who cares about 2% or 3%? Everybody see what I'm talking about? Yes? So don't worry about it. It's acceptable. This is code, actually. This is what they ask you to do. Is that correct or not? Yes? Now, what happened here is this. Okay. So on the top, we have, let's go back again this. On the top, this is the, on the top, I have only normal stress, no shear stress. Is that correct or not? Here, I only have shear stress, no normal stress. However, this point becomes very critical. This point, let's call it point B. I call it for other class, so I use the same thing. That point B is very correct, and you have to check that point for a stress, for principal stresses. Check point aside from top and bottom, because on the rectangular shape, we said check only bottom and top. For wide flange beam, you check the top and bottom. You check the middle for this thickness. You just do the middle top max. I'm going to show you an example for that one. So its design is complete. However, aside from this point and that point and that point, this one for shear stress, this point for normal stress, yeah, that's because this is what you learned before. But however, you should check this point for combination of normal stress and shear stress. Notice normal stress is a little bit on the top. On the top, shear stress was 0, yes or no? But at this point, you have, this is what I'm saying, that on the top, you only have this tension or in compression. A little bit below that, that's at this point B. At that point B, you have a normal stress. This sigma B is less than sigma top. Is that correct or not? However, suddenly you have this shear. Is that correct or not? Because look how much shear showing here. You see, you're showing this shear. Is that correct or not? So if I put that shear here, tau, at that point, so it may go like this or opposite. As you see, this can give me a principal, sigma principal, which is larger than sigma top. Everybody understand? So crack, instead of appearing on top, it's usually, actually, this is always the case. It appears from at the connection of the flange to the weld, especially if during the design you choose a beam which is very tall and very narrow. You see that you have different options there. So if you really make it too narrow, this is what's going to happen. You become greedy and say, I want to save money. Everybody understand, I have no restriction on the top, so I make it very top and very narrow on the T. Everybody understand that exactly that's what's going to happen. That point is going to break first before. Occasionally this happens. So that's all I'm saying that. For the rectangular, I'm summarizing. For rectangular shape, only top and bottom, but based on the Mohr circle. For rectangular, for the wide flange beam, top and bottom, and of course, this point, and the connecting point. Now let's go to the problem I showed you previously, and we design it together. Let's refine that design. You see the whole idea. We designed this beam in now ME 218. Actually, I did it before for you as well. Is that correct? I designed this beam for you based on 218 information. How did we do it? Anybody remembers? I gave you a couple of homework, 2, 3 homework, and I asked you even in the quiz. One of your quiz was the design of the beam, wasn't it? Yes? Earlier quiz? Yes? Was it or not? I don't remember.
No, it was last.
It was ME218, or it was homework, first homework. Yeah, first homework. Do you recall that? Let's do it again. I mean, we forgot that. This is the loading, yes or no? This is the shear diagram. This is the moment. First of all, where is the shear maximum? Shear is maximum at this point, yes or no? Moment is maximum at this point. What's the value of the moment? It's hard for you guys to see, but the maximum, well, I can make it a little bit larger. Of course, you have your handout. This is for the purpose of the, let's do it that way that we can, okay. All right, so can you see it? Mohammed, can you see it better? Is that correct or not? Yes? All right, so as you see, we designed this beam. Let's go through the process together one more time and see what we have to do extra based on this discussion that I had with you. Okay, now let's go that. Let's first of all say sigma allowable, this is what I gave you before, equal to 12 KSI or 12,000 PSI. Let's assume tau allowable equal to 6 KSI or 6,000 PSI. And let's design this beam. Already I did it in class for you, but for today's discussion, I have to do it one more time. Is that correct or not? Sirs, what we did and what you did previously, you check the top, yes or no, or the bottom. The moment is at that section, look at section E. You have a moment M here, and the value of moment is 9,600 pound-foot, I believe. Yes or no? Don't forget the unit, because that unit makes a big difference. Correct? 9,680, correct? So then we said this. We have sigma equal to M over S, S being I over C. We recall all of that, yes or no, correct? Then we said S equal to sigma over M. In this case was sigma, oops, sorry. No, other way around. So S equal to M over sigma or equal to M. Magnitude. Again, tension or compression doesn't matter. So it is 9,680 C over I is us times 12 become pound inch divided by 12,000 PSI or pound per inch square. So the result, pound on pound drops out. The result will be in inch to the power of 3. We went through this process together, I recall. Is that correct or not? I gave you a handout from ME218, yes, pages 17, 18, 19 from the book. And this becomes 9.68 inch to the power of 3, yes or no? Then we went through the table. I don't recall what we got, but I have it here written somewhere. I remember from the other class also. So let's take a look. Anybody remembers what we end up with? You remember we did all of that. Yes or no? Okay, look at your note. When you go home, take a look at it. This is repeat, guys. I don't have that luxury, but we went through bottom up from the paper. We choose 3 or 4 of them. We end up W813 to be the best choice. Why? It was the most economical choice because it has the less weight. Remember we did that and you did it in your homework. Is that correct or not? Yep. So that is what we did based on our information through ME 218. Now we have a little bit more information. Let's look at it. I said we need to check this point, yes or no? But do I need to check it at point E? Do I need to point that point at point E? Look where it is. This is the top. This is the bottom. This is the connection. Do I have any shear force there?
That's the connection.
Not at point E. That's the whole thing. You see, you cannot make that mistake. You see, this is all discussion is based on the shear diagram and moment diagram. Yes, I said we have to check that. That's exactly what the student make a mistake. That's what the student make a mistake. They put that this is shear max, this is moment max. They put the moment max and shear max at the same time. Is this true? So I have to design my beam based on shear and moment diagram. Everybody understand what I'm saying? Yes, if at this point I have this much moment and that much shear, then I put it together. That's no problem. But is this the case here? So look what I'm drawing here. See, at this point, there is no combined stress. I only have normal stresses, all principal stresses. Forget about it. Is that correct or not? Now let's go to the other point. What other point did I check already? Remember, I did not check. Let's do the other check. The other check you want to do is maximum shear. The maximum shear according to that equation. Yes or no? Yes, where is maximum shear in the vertical plane in this plane? Is going down, where it is at the middle. But it is not at this section E, it is at section D. Is that correct or not? Yes? So let's draw the section D. So far, look what I'm saying that. This is the section we have. This is section E. At section D, this is section D. You only have a negative shear. Negative shear is going up, not down. But sign, as I said, is not important. Is that correct or not? So how much is tau max here for at this point? Tau max equal to value of the shear, which is 200 pounds divided by area of the web. Area of the web, look. You see, area of the web. I just gave you the formula. Is that rather than using VQIT, which is not possible to you, because these are curved like that, these are curved. Everybody understands that. When you buy it, it's like that. You cannot calculate the Q, by the way. You have to use this equation. Is that correct? And that's the code. That's the standard code that everybody uses. Is that correct or not? Yes? Therefore, what you go there, you go to this section, you look for the depth. The depth should be about 8 inches, yes? But actually, when you go there, you will see that it is 7.99 inches. Then you go find the thickness of the web in the table. These are all in the table because you have chosen this from the paper, Appendix A. Is that correct or not? I gave you all those that. The thickness of the web, or this thickness, ends up to be here. I calculated for you. You have to go through this homework that I will give you or have given you about the beam design. This is what you have to go through, guys. You see, that's what I said. Don't go ahead until I explain it to you. Is that correct or not? What you were doing, perhaps, you were using the same standard as ME 218. You did that? Good. So that you are ahead of me then. Then if you read it and you understood it, that's perfect. Is that understood what I'm saying? That, but some people already have done even the shaft design, which I haven't explained it yet. But that's good for them. Is that correct or not? But I'm giving you everybody all the detail. Divided by thickness of the web. That in this case, I calculated that here. Thickness of the web is 0.23, so the stress become 1,197 psi at that point vertically, which is like that. Everybody, this is the tau. So if this is the state of stress, that's the tau. Is that correct or not? Yes? Correct? And then, in other words, this is the tau, then you finish it like that. And that tau is 1,197. Correct? And no normal stress because it is on the neutral axis. Yes, sir. Correct? Yeah. But however, since this is less than 6,000 psi, which is my sigma allowable, then I'm okay. Is that correct or not? But is this the highest or principal stress, et cetera, et cetera? Is that correct or not? Now, I need to check this. I asked you to check this point, didn't I? Yes or no? Where is that point? Where should I check it? We decided not here. We decided not there. Obviously not here, because here this is moment is 0, shear is 1800, yes or no? 1800 is less than 2200. Why do I want to check that? I already checked it for 2200. It was okay. I still have much more room. Look, the shear stress is that. So where should I check that connection point? Anywhere in this B. Everybody see that? At B, you have 9,000. Granted, it is less than, no, but this one, 968, is associated with 0 shear. Yes or no? This 9,000 is associated with how much shear? Not 300, with, because you are left of B. On the left of B, you have 9,000 stress, moment, and 1,800 shear. So let's check that point. Is that correct or not? Everybody getting the idea that this is all based on your shear diagram and moment diagram. If you have a combination, you have to check it. That's all I'm saying. If you have one, you already checked it. One alone is already been checked. Yes. You have to check that one too. Yes, B or C. Is that absolutely good question? If I were you, I would check both B and C. Since I don't have time, I only do it B for you. So you do the C yourself. But you have to, that's exactly what you have to do if you want to be sure that every part of this beam is safe. Absolutely, good question. That's exactly my point. You have to look to see, because this one is more than 9,000, but it's less shear. That combination also may give you that result. However, look, it is much simpler than that. So you don't have to do too much work. You see that? Let's go to that section. Now we are at section B. Yes or no? Yes or no? Okay. What's the moment? 9,000. What's the shear? Plus or minus? So that's the shear. Is that correct or not? According to the shear moment and shear diagram. Correct? Yes? However, do I need, this is the top point, this is the bottom point, this is this point, and this, I said here, 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 and here. Yes or no? Do I need to check the top? Come on, guys. Do I need to check the top? No. Very good. Because effect of shear on top is 0. And this 9,000 is less than 968. So that's not the key here. Actually, you see, I'm doing that for the connection point. Is that correct or not? Since effect of this on top is 0 and 9,000 is less than 968, who wants to check on top? Obviously, 9,000 will give me less stress. Yes or no? Do I need to check it here? No. Because effect of this 0, this is 1,800. I already checked it for 2,200. So I don't want. The only point I want to check actually is at point B. Is that correct? So let's find the stresses at point B. Absolutely. So here is point B. Now you have to go back again to ME 218. Sigma at that point is equal to compression. That doesn't matter. Again, compression or tension doesn't, because it's similar top and bottom. It's M. M is 9,000 times 12. Yes or no? Correct or not? Yes? Times what? Times C? No, not C. Times? Come on, guys. Is that your y? Yes or no? Type y, my. So what I'm calculating here, guys, sigma equal to minus my over I. Yes or no? Because we are not on top, we are not on the bottom, we are at the connection of the web to flange for this combination of the load. The combination of the load is here. No need to, this is already been checked, this is already been checked. This is the only point I need to check for that combination. So 9,000 times y, if you go to the table, you will see that is that distance here. The total depth was 7.99. So 7.99 divided by 2, which is half of the distance, minus thickness of the flange, which is 0.255. So that is this y. Divided by I, you cannot use S anymore because that's not, S is for the top and bottom. This is I from the table become 39.6 KSI, and this stress become minus 10,200 PSI. On the top was near 12,000, but this is 10,012. However, I have a shear stress there too, yes or no? Mm-hmm. And the shear stress will be calculated based on that formula, yes? So shear stress at that point, in other words, this is what we are trying to do, guys. Here, look at the point here. I hope you understood everything we did in the past. You have here a normal stress and you have here a shear stress. Yes or no? This is point B, correct? Yes? Normal stress is this much. What's the shear stress? The shear stress, according to the formula, shear force over area of the web. Yes or no? But this time, the shear force is not 2,200. The shear force is 1,800 pounds divided by the same area. We had it there over there because I don't have to repeat it. I just used it a while ago. And that one become equal to minus 900 psi. So this is the state of stress, minus and minus. Everybody understand that. Now I need to check only the principal stresses. Yes or no? That principal stress, if exceed 12,000, then I'm in trouble. Everybody understand that because principal stress cannot exceed the 12,000 that I had. Is that correct or not? Because sigma allowable, I erased it. Sigma allowable was equal to 12,000, correct or not? But check it, you see that. But you don't have to go through the whole circle and plot it. All you have to do at this stage, calculate sigma average. By the way, sigma average is half of that. Everybody understand what I'm saying? That sigma average is minus 5,100 psi. Is that correct or not? Yeah. Then you have to calculate R. Everybody see what I'm talking about. Very simple. I'm not going to do it because I'm running out of time. You calculate R. Then sigma principal 1 becomes sigma average plus R or sigma average minus R. And if you that is less than 12,000, you are okay. If it's more than 20,000, you have to pick up a larger size or another section in the leaks. Is that because you picked up very narrow one probably? Is that correct or not? That's what I said when we designing ME 218. I mentioned, I don't know whether you recall or not, or earlier in this class. There is more to it than what you see there. That's the explanation. Is that correct or not? Yes. So you do it, of course, as a friend of us back said, either for B or C or for both of them. Everybody understands. So there are several points to be checked to be sure everywhere is safe. Is that correct or not? Yes? Next. This is done. Any question? Yeah.
Just make sure for area of web, does it stop?
Go all the way.
All the way top of bottom?
We consider the shear stress on the web, but as far as calculation of it, we go all the way. Okay. But still, we consider here 0. Notice here is 0. Here is max, but we just for the design, I don't know, because they said this is too much, so they modify that. You know, they just put a little bit more detail. Okay. You understand that? Yes? But the shape is like that. Okay. Now let's go to the design of the, now what I just told you is what the process of design is. Now in the shaft design, we have to go through that process. So let me establish the criteria there. We don't need that. Let's put that one up. We don't, I need the board. So let's do that and not forget this. Let's say that before I go through the shaft design, I want you to show you what is going to happen. This is a very interesting problem as far as your future courses is concerned. When you go and you want to design something, you have to follow a certain process that you have heard me or your instructor in ME 218 or so far in ME 219, which is me. I have told you pieces here and there, but let's put everything together. Let's say what we said that. We go to design process. This is what you have to do, guys. In the design process, you have to go through certain steps that we just were discussing it. Let's summarize that. It's not in the book or any book, so you want to write it. This is just my own system, just trying always to bring this information to the student as best as I can. Is that correct? You want to design something, okay? The first thing that you want to know, of course, is what are you designing, and basically that what are you designing gives you the loading. So if it is a beam, you need the load on the beam. If it is a column, you need load on the column. If it is a shaft, you need the torque. Is that correct or not? So that is the design idea that you have to immediately decide in the first step. Without that, you cannot start any problem. That's why I said the static is very important. Those loading comes if you have a structure or your system or design of frame of the airplane, you want to see what kind of the load applied there. Is that correct or not? Second, what kind of material we are using. Then immediately you have to, as you cannot go any further, to decide what kind of material you want to do. What that gives you. That gives you what's material? What we discussed that all in detail in ME 218 again. Material gives you what? Modulus of elasticity, because you need all of that for E, stress, it's a modulus of rigidity and Poisson ratio and alpha. What's alpha? You remember the alpha. Alpha was coefficient of thermal expansion. We used it for temperature because that could be a problem. Is that correct or not? Yes? Especially for mechanical engineering. Then what do you do next? Step 3. Okay, I have my loading. I have my material. Then what is my next step, logical step from what you have learned so far? What? Beam. What are you doing the beam? See, that's exactly. You just think about what you have done, and this is the idea of engineering work it is. Okay, we went through lots of things, do this, did that. Do you understand why? That why should be now very interesting for you. Is that correct or not? Why did we draw the shear and moment diagram? Everybody knows the answer. To maximum moment and maximum shear. But so we want to calculate the maximum, correct, maximum M, what else? Shear, what else? T, what's the torque? Is that correct or not? Remember in the torque shaft, we have to go through the shaft from beginning to end, find out torque here, torque there, torque there. Is that correct or not? There are always not one torque. There are several torque applied. Is that correct or not? Somewhere the torque become the highest value. That highest value give, because I need that to find my stresses. Yes or no? Correct? First, I need to calculate shear and moment diagram and torque diagram has nothing to do with the size of the thing. Have you noticed that? It only depends on the length, which we already know. We have a beam or we have a shaft. Okay, this is the shaft sitting on some bearing. Then I have a torque T1 here. Then I have a torque T2 here. Then I have a torque T3 here. Obviously, T3 must be equal to T1 plus T2. There's somewhere in this shaft torque is maximum, but probably is here. Is that correct or not? Everybody see what I'm talking about? If this is 5, this is 10, this is 15. Yes or no? So that's where the torque is. So you do the same thing for the shear and moment diagram. Sometimes it was necessary, sometimes it was not necessary. When it is necessary, you draw it. If not, you just go to the where these are maximum. If I give you a cantilever beam, this load and this load, where do you go for maximum M? It's obvious to you. You go here because you don't draw the shear and moment. Why at that point M is maximum? Is that correct or not? Somewhere else shear is maximum, as you saw it in previous example on the board. Yes or no? So you determine this. Now, based on this, now you have to go to the next step. What's the next step? Calculating stresses. You went through ME 218 for 10 weeks. With all the headache that you went through to do that part. What was that part? Calculating sigma and tau. Is that correct or not? But before you do that, this is what you do. That you calculate this based on most. No, I did no. Let's go to that. Let's cut that. Then you calculate sigma equal and tau. What is sigma equal to? We went through that together many times. Sigma equal to, I don't want to write it down here in detail. Sigma equal to plus minus N over A, not P. Remember, N over N is the normal stress. Is that N over A and plus minus M, 1 or 2M, 1M, everybody understand it. And torque was, the tau was the result of TC over J or VQ over depends whether it's beam, a shaft, or what, or a combination. Is that correct or not? All those pipe, you had all of that. Is that correct or not? Okay, what do you do after that? Now, where do you calculate this? This is the whole point. No, not yet. You are ahead of me. You're getting there. All right. Where do you calculate this sigma and tau? Okay, this is the shaft. Do I calculate it here or here or here? Most critically, maximum. And more of that is this. Look, this is not all that. This sigma t, if the cross section is like that or like that, where the sigma is maximum, that's what we were talking about, yes, a minute ago. The sigma will be either on top or on the bottom. Or here the torque is somewhere, the shear is here, etc., etc. Is that the case? And we found out the stresses here and here and here and here are different. Is that correct or not? So you calculate this one. We generally call it for most critically stress point. I don't know whether you remember your homework. One of your homework, I asked you to calculate the stress at point H, and I said, ask you to for point K, and I said, which one is more critical? Draw the force circle for that one. There was a reason for it. That's the reason. Is that correct or not? Do you understand what I'm saying? That everything that I asked you is right there in front of you. Is that correct or not? Yes? So in other words, in the section that you have come up with, let's say you have a pipe like that, and there is a force here, there is a force. Remember what we did that here? Then in that section, maybe on top or here, the stresses are maximum. You go to that point. Then do what you do afterwards.
More circle?
Of course, you do the more. This is to get to this point, this is a static. From here to here is ME218, yes or no? And chapter 1 to chapter 6, yes or no? Now we go to chapter 7. And chapter 7, calculate what? Calculate the principal stresses. Very good. Not and maximum shear. Not maximum shear. What shear? Absolute maximum shear. So you put it for this most critically stressed point, which is the stresses being the highest value in entire beam or shaft or a structure. Is that correct or not? Yes? For that particular put, use, Mohr circle to find what?
Principal stress.
Yeah, to find, sigma P1, sigma P2, and sigma P3 is equal to 0 for plane stress. And what? And absolute maximum tau. This is what, which means you should consider R3 circle. Yes or no? Yes. Okay. Then, what we do afterward? Look what I did in previous beam. Didn't I give you sigma allowable? Didn't I give you tau allowable? What does that mean? How do we check to see whether our beam or shaft is safe? So this one of this one, let's assume sigma principal 1 is larger than sigma principal 2. One of them is larger of the two. Remember when you draw the circle, one is maximum, one is minimum. Doesn't matter whether it's tension or compression. Some people assume when it's in compression, it's less. I saw one of the students doing that. If sigma tension is 100 psi, sigma compression is minus 2,000 psi. Minus 2,000 is much more dangerous than 100. That's the max. Everybody under max is not magnitude. Everybody, it's just either it's tension or compression is the same. It is in magnitude. You have to call the magnitude, not number-wise. Of course, 100 is always ahead of minus 2,000. When you owe minus 2,000 and you have $100, you are that much ahead. Is that the difference with 2,100? Yes or no? Correct. But we are not talking about that. The point for a structure is minus 2,000 compression is much more dangerous than 100 psi in tension. So that's what we are talking about. Let's say sigma PAY is equal to sigma PR, and then let's say we calculate that. Then what we do here? Then we say sigma PA1, that's exactly what you want to, should be less than sigma allowable, and tau absolute. Tau max should be less than tau allowable. Correct or not? First of all, suddenly you are facing two criteria, not one. Which one should I use? That one, I cannot tell you. Actually, I tell you now the story behind that. That one, if you want to decide which one of them, because this gives you one size, this gives you another size. Totally, they are not related to each other. Everybody said that. One is criteria of the shear, the other one is criteria of normal stress. In order to understand that, remember this phase, that's the sentence that I'm telling you. This was part of ME219 some years ago, about 10 years ago, 8 years ago, I don't remember exactly. This was part of ME219 to discuss the failure theory with you. The failure theory shows you which one of these two is more critical, what's the interrelationship between the two. There is a maximum shear stress theory which considers this into account. Then there is maximum distortion energy theory, which considers the normal stress. There are several theories, very expanded. A short format of it is in the book, but somehow they took that out of ME219, put it in 319. So some of you who are taking 319, remember that part of a 319 will be about the failure theory, which discusses the relationship between these two. Everybody understand that. In this class, because I know that for the fact, most of our items are going to break because of shear, not because of normal thing. We are going to use this one. So this is the only one we are checking. So please write it down. As you see, I don't know whether you noticed that none of you came to my office, asked about that. In every problem, it says use it based on maximum shear stress theory. Everybody understands it's very important. That means we are not checking the principal stresses. We only checking the maximum shear, because that is 99% of the time for our type of analysis. That's what's going to happen. Is that correct? Which is beam, simple shaft. Is that correct or not? Yes? So that's us. So we are not checking that. And then, okay, we do that. Then what happened at step 7? Let's say that at step 7, we check this one, which is the failure theory. So you just put it there, failure, using failure theory. And then we decided some of this is not what I wanted. I calculate by absolute tau max, and tau allowable is 6,000, that this is equal to 6,000. Now, what I skip here, which I should have put it here, really is, which was very important. In order to calculate sigma and tau, before I calculate, I don't want a size of the object. Yes or no? So actually, there is one more step here. I'm sorry, you have to add that. That's why I end up short here. Here, you decide on size. And when you have the size, that means you have the radius, you have the height, you have the width, et cetera, et cetera. Is that correct or not? Yes? So let's say we are talking about the shaft design now. So in the shaft design, let's say I decided the diameter of 2 inches. Is that correct or not? As an example, yes? Then I go through, because without the diameter, I cannot calculate the tau. Everybody understand what I'm saying? Then I cannot process that. So without this cross-section of the beam, I don't have any eye. I don't have any area. Everybody understand what I'm saying? That in order to do that, I have to calculate that, come to this point. Suddenly, I found out that my absolute tau max is 8,000, and I have only 6,000 allowable. What did I do wrong? My size is too small. That's right. So I have to go back. So this process, so called this 4 and this one 5, sorry for that, 6, and that one 7, so we don't need that. That's based on, this is based on failure theory. Between step 4 and step 7, you have to go back, repeat the process with a larger size. This side, you decide a 3 inch. You go down, then suddenly you find this is 4,000 and this is 6,000. So it is too big. So because you want to save people money, yes or no? You don't want to go from 2 inches to 6 inches. Then you have to decide on 2.4 or 5. So this is going to be trial and error sort of thing. So you decide on the side, you go check. It is either too big or too small. Then you go back again, and this is very headache type of design. Is that correct? So try that for a simple beam. You know what I'm talking about. Is that correct? Now, I'm running out of time, so I have to go be somewhere, so I don't want to go over time. Now, next time, I am going to do this process for the shaft. But the beauty of that is this. If you take carefully, I'm going to do all of this and give you one formula for all 7 steps. Everybody under one formula for the design. Take care of everything, including the Morse circuit. That equation, I have to give it to you, but it is based on the understanding of the Morse circuit again. I did it for the other class, but I'm sorry, I ran out of time here. So we are going to finish that for half an hour. Another example, which is more sophisticated, double bending. I'm going to go to double bending.